Welcome to Late Night History. Settle in, let the lights go low, and let the day fall away from you. Because tonight we are going to travel somewhere no light has ever reached, and no living thing has ever gone, and no one ever will. We are going down. Not down the street, not down a mine shaft, not even down to the bottom of the sea, though that is where our story begins. We are going down through the floor of the ocean, and then through the rock beneath the floor of the ocean, and then down and down past every depth you have ever imagined, until we are more than 600 kilometres beneath the surface of the world. In a place so hot and so crushed and so utterly still that nothing there should ever move suddenly at all. And yet, one day, it did. Let me set the scene for you slowly, because there is no hurry here. There is no hurry anywhere in this story. It is a story measured in millions of years, and a few seconds of it will do us for tonight. Off the far eastern edge of Russia, past the long curving arm of the Kamchatka Peninsula, there is a cold grey sea called the Sea of Okhotsk. On the surface it is an ordinary sea. Ships cross it. Ice forms on it in winter and drifts in slow pale sheets. Fishermen work it. Above it the sky does what skies do. But directly below that sea, straight down through the water and then through the crust, and then deep, deep into the body of the planet, more than 600 kilometres down, there is a place where the rock should have been sleeping forever. A place where, by every rule we thought we understood, nothing should ever break. On the 24th of May, in the year 2013, it broke. At a depth of around 609 kilometres, the rock down there tore itself open in a single enormous rupture. A rupture that released as much energy as one of the largest earthquakes our planet ever produces. In the language of scientists, it was a magnitude of about 8.3. It is to this day the largest deep earthquake ever recorded by human instruments. The very largest out of all the deep ones ever measured. And here is the first strange, quiet, wonderful thing. The thing that makes this whole story worth losing a night's sleep over, or rather, worth falling asleep to. That earthquake, that enormous shudder 600 kilometres down in the dark, harmed no one. It knocked down no buildings. It raised no wave. It killed nothing and toppled nothing and buried nothing. Most of its vast energy was swallowed by the hundreds of kilometres of rock lying between it and the world above, spent and softened and lost in the deep mantle before it could ever reach the surface where people live. But it did travel. Oh, it travelled. Faintly, gently, like the last ripple of a stone dropped in a still pond an hour ago. That tremor spread outward through the whole body of the earth, and it was felt, ever so slightly, by people in the city of Moscow, roughly 7,000 kilometres away. Think about that for a moment, in the slow way we are going to think about everything tonight. Something snapped at the bottom of the world, in a place no drill has ever come close to reaching, and a person standing in an apartment in Moscow, thousands of kilometres to the west, could feel it under their feet. The planet rang, softly, like a struck bell, and the sound of it was old rock breaking, where old rock is not supposed to break. So let me ask you the question that this whole night is built around. It is a simple question, and I want you to hold it gently in your mind as you drift, because we are going to answer it slowly from every side over the hours ahead. How can there be an earthquake 600 kilometres down? Because down there, at that depth, everything we thought we knew about how earthquakes happen falls apart. Down there, an earthquake should be impossible. Let me tell you why. And I promise to keep every word of it easy, because there is nothing here you need to strain to understand. This is not a lecture to stay awake through. It is a slow walk downward, taken hand in hand, and if you fall asleep halfway down the staircase, that is exactly as it should be. The staircase will still be here. The rock has waited 100 million years. It can wait for you to wake. But before we take the first step, let me do the small warm thing I like to do at the start of these journeys. I would love to know where in the world you are listening from tonight, whether it is raining on your window or snowing or perfectly clear, whether it is late evening or the small hours of the morning, whatever quiet corner of the planet you have made your bed in. Leave it in the comments if you feel like it. I read them, and there is something lovely about picturing all of us, scattered across the surface of this restless, breathing world, lying still in the dark together, while beneath every single one of us, the deep rock turns over in its ancient sleep. And if you are new here, and you would like more slow journeys like this one to carry you off at night, you are very welcome to subscribe and stay a while. There is no rush to decide. There is no rush to do anything at all. Now, let us take that first step down and understand why what happened beneath the Sea of Okhotsk should have been impossible. Everything most of us have ever heard about earthquakes describes something that happens near the surface. Two great slabs of the Earth's outer shell, two plates, grinding past each other. They catch. They lock. They strain against each other for years, for decades, building up a slow, enormous pressure until finally the friction gives way all at once, and they lurch, and the ground shakes. That is the picture almost everyone carries. Rock rubbing against rock, catching and slipping, like two rough bricks dragged across each other, one of them suddenly jumping forward when the grip finally lets go. And for the earthquakes we know best, the ones near cities, the ones that make the news, that picture is more or less right. Those are shallow earthquakes. Scientists draw a line and say that shallow earthquakes are the ones that happen in the top 70 kilometres of the Earth, from the surface down to about 70 kilometres deep. That is where almost all the famous, dangerous, destructive earthquakes live. Right up near the top, in the crust and the very uppermost part of the layer beneath it, where the rock is cool and stiff and brittle, and where 2 blocks of it really can catch and slip and jolt the world above. But earthquakes do not stop at 70 kilometres. They keep going deeper. From about 70 kilometres down to about 300 kilometres, we find what are called intermediate depth earthquakes. Deeper than the crust, well down into the mantle, the thick hot layer that makes up most of the volume of the Earth. Already, at those depths, things are getting strange, because already the rock down there is warm enough and squeezed hard enough that the simple picture of 2 bricks rubbing together starts to run into trouble. But the intermediate ones are not even the deepest. Below 300 kilometres, and reaching all the way down to about 700 kilometres, there is a third kind. These are the deep focus earthquakes. The deep ones, the subject of our whole long night, 300 kilometres down to roughly 700 kilometres down, and then, quite abruptly, they stop. Below about 700 kilometres, in all the decades we have been listening to the planet with our instruments, we essentially never find a single one. The deepest reliably recorded earthquakes reach down to something like 700 kilometres, and then the Earth goes quiet. Whatever is happening down there, it draws a firm line at around 700 kilometres and refuses to cross it. That line, that sudden silence, is a clue, and we will come back to it later when you may already be asleep. So there are our 3 floors of the house, if you like. Shallow, from the surface to 70 kilometres. Intermediate, from 70 to 300. And deep, from 300 all the way down to about 700. The Sea of Okhotsk earthquake at 609 kilometres was firmly, profoundly, in that deepest basement. Not just a deep earthquake, but the greatest deep earthquake we have ever recorded, breaking near the very bottom of where earthquakes are able to be at all. And now here is the puzzle, laid out plainly. The deeper you go into the earth, the greater the pressure. This is easy to feel in your bones, because you have felt a small version of it. If you have ever dived to the bottom of a swimming pool, you have felt the water press on your ears gently, insistently, go deeper into the ocean, and the pressure grows so great it would crush a submarine. And rock is far heavier than water. So as you sink into the body of the earth, mile after mile of rock stacking up above you, the weight of all that rock bears down harder and harder on everything below. By the time you reach 600 kilometres down, where our earthquake happened, the pressure is almost beyond imagining. Scientists measure it in units called gigapascals. And down there, the pressure is somewhere around 20 to 24 gigapascals. That number will mean nothing to you, and it should not, so let me turn it into something you can hold. 24 gigapascals is roughly 200,000 times the pressure of the ordinary air resting on your skin right now. 200,000 times. The air around you, the air you are breathing as you lie there, presses on you gently from all sides, and you never notice it, because you were born inside it and you have carried it your whole life. Now imagine that same pressure multiplied 200,000 times over, squeezing every direction at once, squeezing so hard that there is no gap, no crack, no pore, no empty space anywhere. Everything pressed together into one solid, seamless, crushing embrace. And it is not only crushing, it is hot. The rock down at 600 kilometres is somewhere around 1500 to 1600 degrees. Hot enough that, given time, rock does not behave like the hard cold stone you know from the surface at all. Down there, under that heat and that pressure, rock behaves more like something soft and slow, something that flows. This is the part that surprises almost everyone, so let me linger on it, gently, because it is the heart of the whole mystery. We think of rock as the very definition of hard, solid as rock, we say, set in stone. But rock is only brittle and hard when it is cool. Heat it enough, and squeeze it enough, and give it enough time, and rock will bend and creep and ooze like something halfway between a solid and a thick liquid. Not melted, not liquid. Still solid if you touched it in an instant, but over long stretches of time, under that heat and pressure, it flows. The everyday picture I like best for this is a very thick, cold jar of honey. If you have ever tried to pour honey that has been sitting in a cool cupboard, you know it does not want to move. It clings, it stretches, it comes out in a slow golden rope that seems almost solid. Poke it quickly, and it feels firm. But leave the jar tilted, walk away, come back later, and the honey has quietly flowed to the low side, all on its own, in no hurry, simply following the pull. Warm rock, deep in the earth, is a little like that. It is far, far stiffer than honey, unimaginably stiffer, so that its flowing happens over thousands and millions of years rather than minutes. But the principle is the same. Down there, rock should not snap. It should ooze. It should bend and give and slowly reshape itself around any strain, the way warm honey settles, the way warm wax sags, the way anything soft and slow yields rather than breaks. And that is the whole problem. That is the impossibility sitting at the center of our night. An earthquake is a snap. An earthquake is rock breaking, suddenly, all at once, releasing in a violent instant a strain that had been building slowly. But rock 600 kilometers down is not supposed to be able to snap. It is supposed to be too hot and too squeezed to break. It is supposed to flow quietly, releasing any strain the gentle way, oozing it out over ages, never storing it up, never letting it burst. So how did it break? There is a second half to this impossibility, and it is worth understanding, because it closes the door even more firmly. Even if you set aside the flowing, even if you imagine the rock down there were somehow still brittle and cold, our old picture of earthquakes still would not work at that depth. Remember the two bricks rubbing together, catching and slipping. That kind of earthquake, the kind we understand best, depends on friction. It depends on two surfaces being able to slide against each other, to catch, to lock, and then to suddenly let go. Scientists have a name for this ordinary kind of breaking. They sometimes call it brittle failure or frictional failure, the sort of thing that happens along a crack or a fault where two faces of rock grip and then slip. But friction has a weakness, and the weakness is pressure. To slide two rough surfaces past each other, they first have to come apart. Just a hair, just enough to move. A crack has to be able to open, even slightly, for the two sides to shift. And the immense pressure deep in the earth does not allow that. That 200,000 times pressure presses in from every side at once, and it clamps every possible crack shut, closed, sealed, welded tight by the sheer weight of the world above. You cannot slip two faces past each other when something is squeezing them together with the force of a mountain range. The pressure holds the fault closed the way a giant hand holds a book shut, and no page can move. So the deeper you go, the harder it becomes for an ordinary friction earthquake to happen, until, at these enormous depths, it becomes simply impossible. The pressure clamps every fault shut forever. The heat makes the rock flow instead of snap. Both rules point the same way. Both rules say the same thing. There should be no earthquakes down here at all. And yet the record is clear, and the instruments do not lie, and the ground in Moscow trembled. There are earthquakes down here, thousands upon thousands of them over the years we have been listening. And the greatest of them all, the deepest great one ever caught, went off beneath the Sea of Okhotsk in the spring of 2013, 609 kilometers down, in a place where rock should only ever bend and flow and sigh, and instead it snapped like a pane of glass. This is the puzzle that seismologists, the scientists who study earthquakes, have turned over in their minds for the better part of a century. And I want to be honest with you, in the calm way this story deserves, about the shape of the mystery. Because the shape of it is part of what makes it so beautiful to fall asleep inside. It is not that we know nothing. That would be one kind of story, a shrug of a story, and it would not be true. We know a great deal. Over the decades, patient people in laboratories and patient people staring at seismograph traces have pieced together a genuine, concrete idea of what might actually be snapping down there, and it is one of the strangest and loveliest ideas in all of Earth science. And I am going to tell it to you slowly over the hours ahead. But nor is it a closed book. We do not know it the way we know that water freezes into ice. There is real, living uncertainty here, an honest, not quite sureness, and part of the wonder of this subject is that even now, tonight, as you lie there are scientists who disagree. Gently. about exactly what happens 600 kilometres beneath your feet. Two of the greatest deep earthquakes we have ever recorded, we will find, did not even seem to break in quite the same way as each other. The mystery is not solved and sealed, it is alive, it is still being worked out. And there is something deeply restful, I think, about a mystery that no one has finished. A question the whole species is still slowly turning over, that will still be turning over long after tonight, long after all of us. So let me lay out the three parts of the puzzle plainly, the three quiet questions that we will follow down into the dark, because naming them will give your sleeping mind something to hold, three smooth stones to carry down the staircase. The first is the question of who, or perhaps of what. What is it exactly that breaks? If it is not 2 blocks of rock rubbing and slipping, because friction cannot work down there, then what actually gives way? What is the thing that snaps, when snapping should be forbidden? Something must fail. Something must break to make an earthquake. But we have just seen that ordinary rock, under ordinary rules, cannot break at that depth. So there must be something else down there, something not quite ordinary, something hiding inside the rock that is able to fail in a way plain rock cannot. What is it? The second is the question of when or how deep, and it is the riddle of that firm line at 700 kilometres. Why do these deep earthquakes exist at all in the range from 300 to 700 kilometres and then stop so suddenly, so completely, right around 700? Whatever the answer to the first question is, whatever thing it is that breaks down there, it must be a thing that is present between 300 and 700 kilometres, and then, below 700, is simply gone, or changed, or no longer able to do what it does. The line is too sharp to be an accident. The earth is telling us something with that silence. But what? And the third is the question of why. Not the small why of the mechanism, but the large why of the whole thing. Why is any of this happening at all? Why is there cold? Breakable material 600 kilometres down in a mantle that should be uniformly hot and flowing? Where did it come from? Because here is a thing we have not yet said, a thing that turns this from a puzzle about rock into a story about the whole slow-breathing life of the planet. The rock that broke beneath the Sea of Okhotsk was not born there. It was not always 600 kilometres down. It came from somewhere. It was carried down, dragged down, sinking slowly into the earth over millions of years, and it brought its coldness and its strangeness with it from far away and far above. And where it came from, and what it is, and where it is going, is the deepest part of our whole night, the part that turns a broken crystal into a story about the planet swallowing its own skin. Who breaks? When it stops? And why it is down there to break at all? Hold those three, if you can, as you drift. And if you cannot hold them, if they slip out of your hands into sleep, that is perfectly all right, because I will carry them for you and hand them back when you are ready. Let me stay a little longer with the sheer wrongness of it, because I think the wrongness is what makes it wonderful, and because there is no better lullaby than a beautiful thing your mind cannot quite finish arguing with. Picture the deep mantle as it ought to be. A vast, slow, hot ocean of rock, hotter than any furnace, thick beyond any liquid you have ever seen, so thick that it moves only over millions of years, but moving all the same, turning over and over in enormous lazy loops, carrying its heat up from the depths and letting it seep away near the top, the way a pot of very thick soup on a very low flame will, given hours, form great slow-rolling cells. That is the mantle, That is the true character of the rock that fills most of our planet. Not the hard, cold stone of a mountain cliff, but a hot, dense, endlessly patient flow. In that world, in that proper deep mantle world, an earthquake makes no sense. You cannot snap a river. You cannot crack an ocean. Strain in flowing rock simply flows away. And into that slow, hot ocean, from above, something intrudes, something cold, something stiff, something that does not belong, a piece of the outer world plunging down into the inner one, still carrying the chill of the surface with it, still hard, still brittle, still able for a while to break. That intruder is the key to everything, and we will follow it down together in the parts to come. But for now, simply hold the image, because it is the image that makes the impossible possible. The mantle, on its own, cannot quake, but something falls into the mantle that can. And where that cold falling thing goes, the earthquakes follow it down, marking its path like sparks all the way to 700 kilometres, and then, when the cold thing finally warms enough to lose its brittleness, the sparks stop, and below that the descent continues in perfect silence. You see already, perhaps, how the three questions begin to lean toward each other. The who, the when, and the why are not really three separate riddles at all. They are three faces of one thing. One cold, falling stranger in the hot, deep dark, and to understand any of them fully, we will have to understand all of them together. That is the shape of tonight's journey. Not a straight line of facts, but a slow spiral downward around a single mystery, the same mystery seen from deeper and deeper, until at last we are standing, in our imaginations, right beside the very grains of crystal that fail, watching them collapse 600 kilometres beneath the cold grey sea. But we are not there yet. We do not need to be there yet. We have all night. Let me leave you, for now, at the edge of the puzzle, holding it lightly. Rock that should ooze like honey, that should bend and flow, and give way slow and soft, that under 200,000 times the pressure of the air and 1,500 degrees of heat should be utterly incapable of a sudden break. Rock with every fault clamped shut by the weight of a whole world pressing down. Rock that, by every rule we thought we knew, should be the most patient, the most yielding, the most unbreakable thing there is. And yet, on a spring day in 2013, beneath a quiet sea off the coast of Kamchatka, 609 kilometres down, that impossible rock gathered itself in an instant and tore open along a wound many kilometres long, and shook the whole planet gently enough that a person in Moscow, 7,000 kilometres away, felt the faintest tremor pass beneath their feet, and harmed no one at all. Rock this deep should bend, not break. So what, then, actually snaps? Hold the question. Let it sink with you. We are going to answer it the way everything in the deep earth happens, slowly, under great pressure, over a long and patient descent, and the first step down, the step we will take together next, leads us to the rock itself, and to a strange and secret thing that happens to a single ordinary mineral as it is carried down into the crushing dark. Because the answer to what breaks, it turns out, is not really about earthquakes at all. It is about a crystal, a common, green, unremarkable crystal, the most ordinary crystal of the upper mantle, that as it sinks deeper begins to change, quietly, into something denser, and about what happens on the day that it refuses. But the crystal can wait. You have come a long way down already, further into the earth in these last minutes than any human being has ever physically travelled. And you have earned a moment simply to rest here in the warm dark, with the weight of the world above you, not as a threat, but as a blanket, pressing gently, holding everything still. The sea is quiet on the surface far above, the rock is quiet in the deep far below. And somewhere between them, the slow machine of the planet keeps turning, in no hurry, as it has for 100 million years, and as it will for 100 million more. Breathe, let the question loosen its grip. We will pick it up again on the far side of your first drift into sleep, and begin to follow the crystal down. The crystal, then, and to understand what it does, and why it matters, and why it is perhaps the most consequential thing happening inside the Earth at any given moment. You need to follow it down from the beginning, from the upper mantle where it lives in abundance, green and unremarkable under pressures that would reduce any surface rock to powder, all the way through the long descent that changes it, slowly at first and then, at a certain depth and under certain conditions, all at once. The mineral is called olivine. Its chemical name, if you want the precise and honest version, is a small arrangement of magnesium and iron and silicon and oxygen, CO. You could hold a piece of it in your hand, on the surface, and it would feel like any other stone, dense, slightly cool, greenish-yellow if the iron content is low, darker and more golden if the iron is higher. The gemstone peridot is a variety of it, and it is found in meteorites, and it makes up the majority of the upper mantle, the thick shell of rock between the crust and the transition zone, stretching from roughly 30 kilometres down to 410 kilometres. In the upper mantle, olivine is everywhere. It is, in a sense, the default rock of the planet's interior. If you could bore a hole straight down and pull samples from the first 400 kilometres of the Earth's inside, most of what you brought up would be olivine, or things closely related to olivine, pressed and heated and altered, but fundamentally the same arrangement of atoms in the same crystal lattice. And in that upper region of the mantle, olivine is stable. The conditions suit it. The pressures there, rising from near zero at the crust to roughly 13 or 14 gigapascals at 410 kilometres, fall within the range that olivine can manage without reorganizing its internal structure. A gigapascal is a difficult thing to make real in everyday terms, so consider this. 1 gigapascal is approximately 10,000 times the pressure of the air pressing on your skin as you lie down to sleep tonight. At 14 gigapascals, the rock is being squeezed by something like 140,000 times atmospheric pressure. And still, in this regime, olivine holds its form. Its atoms arranged in the same tidy lattice they would occupy on the surface, just packed a little closer, a little firmer, under the enormous weight of everything above. But at around 410 kilometres, something happens. It is not dramatic, in the way we usually use that word. There is no sudden collapse, no visible change in colour, no fire. It is, from the outside, entirely invisible. What happens is that the atoms inside the olivine crystal, the same atoms, the same magnesium and iron and silicon and oxygen that were there before, the very same ones, find that they can no longer hold their usual arrangement. The pressure has climbed past a threshold, and there is now a lower energy configuration available to them, a different way of packing themselves together that takes up less space, that is denser, that the conditions of that depth demand. And so the lattice reorganizes. It shifts. The atoms slip into new positions, forming a new structure around themselves, and what was olivine becomes something else, something with the same chemistry but a different internal geometry. The geologists call this new structure Wadsleyite, and it is the first transformation in a cascade that will carry the atoms further and further from what they were on the surface, each step denser than the last. The 410-kilometre boundary, where this transformation happens, is one of the most important interfaces inside the Earth, and we know it is there not because anyone has drilled to it. No drill in existence comes remotely close, but because seismic waves, the ripples that spread through the Earth after an earthquake, travel at different speeds through different materials, and at 410 kilometres, their speed changes abruptly, in a way that tells every seismologist who sees it that something fundamental has changed in the rock below. This is called the 41010 discontinuity, and it marks the beginning of what is known as the Mantle transition zone, a region roughly 250 kilometres thick that stretches from 410 to 660 kilometres down, a realm of extraordinary pressure and transformation where the minerals of the upper mantle are being systematically compressed and rearranged into denser and denser configurations, and where the answers to the puzzle of deep earthquakes are slowly, patiently buried. Inside the transition zone, Wadsleyite does not last forever. As the rock descends further, or as it sits at greater depth, the pressure rises still, and at somewhere around 520 kilometres, another reorganisation becomes favourable, and the atoms shift again into yet another configuration, this one called ringwoodite. Ringwoodite is a spinel-structured mineral, meaning its atoms are arranged in a particular, highly symmetric lattice that is characteristic of several dense minerals and that allows a very efficient packing of the constituent elements. The name honours a geologist called Alfred Ringwood, who pioneered the study of high-pressure mineral physics and who understood, before most of his contemporaries, that the deep earth was not a fixed and static thing, but a place of continuous pressure-driven transformation. Ringwoodite is roughly 8 to 10% denser than olivine. That difference may sound small, but consider what it means for a slab of former seafloor, perhaps 100 kilometres thick and thousands of kilometres across, being dragged steadily downward into the planet. Every cubic metre of olivine that transforms to ringwoodite shrinks slightly, gives up volume, becomes heavier per unit of space. The transformation releases no sound, no flash, no event that any instrument on the surface would record. It happens silently, steadily, as atoms migrate into new arrangements in the dark, and yet it is one of the central events in the internal life of the planet. Because it is part of what keeps the slabs sinking, the denser they become, the more the deep Earth's gravity pulls them down, and the more they pull the surface plates with them at the trenches, and the more the whole slow machine of plate tectonics continues to turn. And then, at 660 kilometres, a third transformation. Near the base of the Mantle transition zone, at a depth of around 660 kilometres, the pressure reaches approximately 23 to 24 gigapascals, and the temperature is somewhere in the range of 5,100 to 1,700 degrees Celsius, and at these conditions ringwoodite itself can no longer hold. Its crystal structure breaks down entirely, not into another variety of the same mineral, but into two separate minerals, bridgmanite, which is also known as silicate perovskite, and ferropericlase. Bridgmanite is believed to be the most abundant mineral in the entire planet. It fills the bulk of the lower mantle, stretching from 660 kilometres all the way down to the core mantle boundary at approximately 2,900 kilometres. And yet it was not formally named and confirmed in a natural terrestrial sample until 2014. This is the depth, the 660-kilometre boundary, that marks the second and final major seismic discontinuity of the transition zone, known simply as the 660, and it is here that the deep earthquake machinery reaches its absolute lower limit. For reasons that are bound up in the physics of this very transformation, in a way we will come back to. So the cascade looks like this, if you trace it from the top. Olivine, stable in the upper mantle, transforms to wadsleyite near 410 kilometres, to ringwoodite somewhere in the transition zone, and finally to bridgemanite and ferropericlase at 660 kilometres. Each step is the same atoms rearranged, like the same handful of letters being shuffled into different words, each word denser and heavier than the one before, each suited to the conditions that the depth demands. The whole transition zone, 410 to 660 kilometres, is a 250-kilometre zone of progressive compaction, a region where the familiar minerals of the upper mantle are patiently converted into the denser materials of the lower mantle, and where the structure of the planet is, in a real sense, being continually remade. And all of this, under ordinary circumstances, happens smoothly. The transformation follows the rock wherever it goes, adjusting the crystal structure to match whatever depth and pressure it finds itself at, so that at any given depth the minerals present are more or less the ones that thermodynamics predicts ought to be there. The Earth has been doing this for billions of years, and the transitions are old and well established, and the result is a mantle in rough chemical and structural equilibrium with itself, depth by depth, layer by layer. But there is a catch, and the catch is the cold slab. When a plate of old oceanic lithosphere, old seafloor, is pushed down into a trench and begins to descend, it carries its temperature with it. Not as a number on a dial, but as a physical reality, the slab is colder than the surrounding mantle, sometimes by a great deal. Oceanic lithosphere, if it is old, if it has been sitting on the surface for 100 million years or more, slowly cooling since it formed at a mid-ocean ridge, arrives at the trench as a slab perhaps many hundreds of degrees Celsius cooler in its core than the mantle it is being pushed into. The surrounding mantle at the same depth might be at 4,100 or 1,500 degrees. The cold heart of the slab, in the most extreme cases, might be only 600 or 700 degrees at that same depth. That is a difference of 500 to 800 degrees Celsius, existing side by side, the cold and rigid slab sliding through the hot and yielding mantle like a cold blade through warm butter. Or, more accurately perhaps, like a slowly sinking sheet of ice moving through water that is much warmer than ice can stay solid in. This cold interior is what makes the slab behave differently from the mantle around it. The mantle, at 1,500 degrees, flows, under the pressures of that depth, over the timescales that geology considers. It creeps and oozes and deforms without fracturing, because it is hot enough that its crystal defects can migrate and its grain boundaries can slide, and the deformation distributes itself smoothly rather than concentrating into a rupture. But the cold interior of the slab has not had time to warm up. It is descending faster than heat can diffuse through rock. Heat moves slowly in stone, and the slab is carrying its cold heart down with it, deep into a realm where everything around it is much hotter, and where that cold should eventually be erased by conduction from the surrounding rock. But the slab is moving, it keeps going, and the cold persists far longer than anything in a warm and uniform mantle would. So here is the situation you have in the cold core of a subducting slab, somewhere in the transition zone. The depth is, say, 450 or 500 kilometres. The pressure is high enough that in the surrounding hot mantle, olivine transformed to wadsleyite long ago, around 410 kilometres as the thermodynamics dictated. But in the cold core of the slab, the transformation is kinetically sluggish. That is the precise phrase, kinetically sluggish. In chemistry, a reaction may be thermodynamically favoured, meaning the end product is at lower energy than the starting material, meaning the atoms want to reorganize, but still proceed very slowly if there is an energy barrier in the way, a hump that the atoms have to climb over before they can settle into the new arrangement. Temperature helps atoms over that hump. Heat gives them the energy to jostle past the barrier, to break old bonds and form new ones. And in the cold core of the slab, there is not enough heat. The transformation that should have happened at 410 kilometres has not happened. The olivine has been carried below its stability field into depths where it should no longer exist as olivine, and yet there it is, still olivine, still holding its original crystal structure, still waiting for conditions that will let it change. This is what is called a metastable phase. And the body of olivine that persists in the cold core of the slab, surviving far below the depth where olivine should exist, is called the metastable olivine wedge. Imagine, if you will, a thick lens of material, cold, unreconstructed, quietly wrong for its depth, riding inside the descending slab like a blade of ice that has somehow not yet melted. Not because the surrounding temperature is cold, but because the transformation requires a warmth that the slab's interior has not yet received, and may not receive for a very long time. The wedge is thickest near the centre of the slab, where the cold is most concentrated, and it thins toward the edges, where heat from the surrounding mantle has had more opportunity to penetrate and drive the transformation. In the coldest and fastest sinking slabs, the oldest and most rigid oceanic lithosphere, the wedge may persist far deeper than 410 kilometres, perhaps to 500 kilometres. Perhaps to 550, perhaps, in some cases, approaching 600 kilometres or deeper, carrying its load of untransformed olivine down through a region where the equilibrium mineralogy is already wadsleyite and ringwoodite, and where everything outside the slab has long since converted. And this wedge is not a theoretical construction. It has been imaged. Seismologists studying the Japan subduction zone and the Tonga zone and the Mariana zone, three of the most intensely studied deep earthquake regions on Earth, have found anomalies in the way seismic waves travel through the slabs in those areas, patches where the wave speeds are lower than expected for rock at that depth, regions that behave seismically. Like material that has not fully transformed, like a wedge of lower density, unconverted olivine embedded in an otherwise denser and more converted slab. The evidence is not perfect, the images are blurry at the scale of kilometres, and the interpretation is always somewhat indirect, but the pattern in Japan and Tonga and the Marianas is consistent, and consistent with the prediction. And it is as close to direct evidence for the metastable wedge as we have. So the picture we have in these cold and fast descending slabs is this: a descending sheet of former seafloor, hundreds of kilometres wide and many hundreds of degrees colder at its core than the surrounding mantle, carrying inside it a lens of olivine that has refused to change, that is riding deeper and deeper below the level where it should exist, held in suspension by the cold that insulates it from the transforming conditions all around it, a loaded spring that is the image, a loaded spring descending quietly through the dark, carrying its unreleased energy down and down, through 450 kilometres, through 500, through 550. Until the cold is finally eroded and the temperature begins to climb, and the transformation, which has been deferred for all that slow descent, can no longer be put off. Quick reminder, after years of lying awake with a racing mind, deep sleep finally became possible. Now learning comes easier, energy is real, and the mind stays sharp. Sleeping like a baby changed everything. If you want the exact system that made this possible, check the link in the pinned comments. And then, the mechanism. Not friction. That is the important thing to hold on to as the mechanism unfolds, because every instinct built from surface earthquakes, from the rubbing of plates and the grinding of faults at the depths where we live, says that an earthquake is about friction, about rock scraping against rock along a fault plane until the stress releases in a catastrophic slip. But at 600 kilometres, friction cannot work. The confining pressure at that depth, 20 to 24 gigapascals, remember, something like 200,000 times the air pressing on your skin, clamps any crack shut with a force that friction-based failure simply cannot overcome. A fault at that depth would need to generate stresses, lateral stresses, that exceed the already enormous confining pressure, and the hot, ductile mantle does not accumulate stress in that way. Whatever happens in the deep to make the earth quake, it is not the sliding of familiar fault surfaces against each other under friction. What happens instead, according to the best and most carefully supported explanation currently available, is something stranger and in some ways more beautiful. It is called transformational faulting, and it works like this. When the metastable olivine in the cold core of the slab finally reaches conditions where the transformation to a denser spinel structure mineral, wadsleyite or ringwoodite, can proceed, it does not necessarily transform uniformly all at once in an even conversion throughout the body of rock. Instead, in certain conditions, particularly in the cold, fine-grained, stressed interior of a descending slab, the transformation can nucleate and run in thin, lens-shaped zones. These lenses are zones where the olivine has collapsed into its denser form, where the same atoms have reorganized into the spinel structure that is 8 to 10% denser by volume. Within these lenses, the rock has shrunk. The volume is smaller, and because the surrounding olivine has not yet transformed and has not shrunk, there is a mismatch, a collapse of the lens interior relative to its surroundings, and this collapse under compression creates something that the physicists and geologists who study it have given a paradoxical and evocative name. They call them anti-cracks. An ordinary crack, in the everyday sense, opens under tension, pull a piece of brittle material hard enough, and a crack propagates through it as the material fails in extension, the two sides of the crack moving apart. An anti-crack is the opposite, it closes under compression. The transformation of olivine to its denser form collapses the lens inward, and the lens becomes, in effect, a zone of failure under compression rather than extension. The anti-crack grows not by opening but by collapsing, by the material inside folding into a denser configuration while the material outside remains as it was. And the material inside the anti-crack, the ultra-fine-grained, newly transformed spinel structure mineral, still warm from the latent heat released by the transformation, is weak, much weaker than the surrounding olivine. It has been chemically converted, but it is fine-grained and disordered, and it does not resist shear the way a well-crystallized rock would. It can slide. And when the anti-cracks begin to form, not just one, not just a few, but many, In a region of stressed and transforming olivine deep in the cold slab, they do not stay isolated. They align. The stress field of the descending, bending slab has a preferred direction, a direction in which compression is most intense and along which failure is most likely to propagate, and the anticracks nucleate and grow preferentially in that direction, and as they grow they approach each other and interact, and their stress fields overlap, and eventually they link. One by one, and then many at once, the anticracks connect into a larger zone of failure, a shear zone running through the weak, fine-grained, transformed material. And because this material is so much weaker than what surrounds it, the shear concentrates there, and the concentration of shear generates heat, and the heat further weakens the already weak transformed mineral, and the zone slides, suddenly and catastrophically lubricating its own failure with the fineness of the material that has already collapsed. This is the earthquake, not friction on a surface, not plates grinding, a crystal collapsing into a denser form and, in doing so, creating a self-lubricating wound through the rock that propagates in the space of seconds across tens or hundreds of kilometres of slab. And the energy of that propagation radiates outward as seismic waves, body waves, the P waves and S waves that carry the tremor through the surrounding mantle, up through the transition zone, through the upper mantle, through the crust, and eventually to the surface, where seismometers translate them into the familiar traces, and scientists read the depth from the travel times, and understand that something has broken impossibly at 600 kilometers down. The name given to this process, transformational faulting, makes it sound dry, bureaucratic, like a technical term that keeps the strangeness at arm's length. But sit with what it actually says. The earthquake is not made of friction, it is made of chemistry. A mineral changing its crystal structure, rearranging its atoms into a denser configuration, and doing so in such a way, under such conditions, that the transformation itself tears the rock open along a self-generated shear zone lubricated by its own fine-grained collapse products. The slab is not sliding against anything external. The slab is, in a very precise sense, tearing itself apart from the inside, triggered by a phase transition that has been deferred for hundreds of kilometers of descent, and that finally, under the warmth it could no longer avoid, runs in the worst possible way all at once, in a thin, concentrated zone. The evidence for this mechanism comes from several directions, and the most persuasive of them came from a laboratory. In the late 1980s and through the 1990s, a geologist named Harry Green and his colleagues set out to test whether transformational faulting could actually work, whether the mechanism was physically real or merely a theorist's speculation. The difficulty with testing it directly is obvious. You cannot put a piece of olivine under 20 gigapascals and 1500 degrees and watch it fail at the scale of a real slab. The equipment does not exist. But what you can do is find a material that undergoes an analogous phase transformation at lower pressures that laboratory apparatus can reach, and test whether that transformation produces the predicted anti-crack failure mode. The material Green's group chose was a compound called MgGeo, magnesium germanate, sometimes written out as the germanate analogue, because it is the germanium-bearing equivalent of the olivine formula, with germanium substituting for silicon. Germanate analogues are useful precisely because the transformation pressures are lower. The spinel phase of magnesium germanate becomes stable at pressures that laboratory equipment can generate and sustain, while the olivine to wadsleyite transition in the real CO requires pressures that only the most demanding apparatus can reach. So Green's group used the analog first, and in their experiments they found exactly what the theory predicted. Under high confining pressure, with the germinate in a metastable configuration relative to its equilibrium transformation, and under the application of stress, they observed the formation of anti-crack zones, fine-grained lenses of the denser phase. And shear failure running through those lenses, transformational faulting reproduced in miniature in a laboratory at pressures and scales that humans could control and observe. And then they went further and did it in olivine itself under the higher pressures required, and the same thing happened. The metastable olivine held under stress at conditions where it should have transformed, failed by transformational faulting. The anti-cracks appeared, the shear zones formed, the mechanism worked. This is why transformational faulting is not merely a hypothesis in the casual sense, a guess, a speculation, an untested idea. It is a hypothesis with laboratory confirmation, a mechanism that has been reproduced experimentally in the material that the real Earth uses, under conditions that model the real Earth's transition zone, and it produces the predicted failure mode. That does not mean every deep earthquake works this way, or that the mechanism is the only one that can operate at these depths. We will come to the complications, to the event that suggests something different or additional may also be at work. But it means that transformational faulting is real, that it can happen in olivine under the conditions of the deep slab, and that it provides, for the first time, a physically coherent answer to the old and stubborn puzzle of why rock that should flow instead breaks. The image that stays with you, or that stays with me, is the anti-crack itself. Not the full earthquake, not the magnitude 8 rupture radiating body waves across the planet, but the very first step, the smallest event in the chain. A tiny lens of olivine, somewhere in the cold interior of a descending slab, at a depth where no instrument will ever directly observe it. Finally losing the battle against transformation, the atoms inside it shift. The lattice reorganizes into the spinel structure, denser, smaller, more compressed. The surrounding olivine holds its shape, and for a moment there is a mismatch, a small and local collapse, an inward failure of a millimetre-scale volume of rock. An anti-crack, one of the uncountable many that will form in the minutes and hours of loading before the shear zone links and the earthquake runs. A single collapse of a single crystal lens, in the dark at 500 or 550 or 600 kilometres down, making no sound that any surface instrument will ever hear, unremarkable in itself. One more quiet step in the long patient chemistry of a planet that has been doing this for billions of years. And then another. And another. And the stress concentrates in the aligned and growing shear zone, and the fine-grained transformed mineral in the linked anti-cracks provides the lubricant. And somewhere in the cold olivine wedge of the descending slab, the chain of failures reaches a threshold, and the zone propagates in seconds across tens of kilometres, and the energy radiates outward in body waves, and somewhere in a seismology station in Moscow or Tokyo or Santiago, a needle moves. And a scientist reads the trace and writes down a depth of 609 kilometres and a moment magnitude of 8.3. And the numbers go into the catalogue, and the mystery of how rock breaks at 600 kilometres gets one measurement closer to an answer. The slab, for its part, does not notice. It continues its slow descent, carrying the remaining metastable wedge further down. The olivine that has not yet transformed, still riding inside it like a blade of unmelted cold, still loaded, still waiting for the warmth and the stress that will eventually run the same process again. Deep earthquakes are not one-time events in a slab. They are recurrent, periodic, happening again and again along the same descending sheet of former seafloor as the metastable wedge encounters the conditions for transformational faulting at successive depths, in successive windows of stress accumulation, over the millions of years that the slab takes to descend through the transition zone and into the lower mantle. But the metastable wedge is not forever, either, as the slab descends and as heat slowly conducts inward from the surrounding mantle and from the exothermic transformations happening at the slab's edges. The cold core warms, and the olivine that has survived metastably begins, region by region, to transform on its own schedule, without catastrophe. Driven now by sufficient temperature to let the kinetics proceed at a rate that does not concentrate the transformation into thin failure-prone lenses, but distributes it slowly and safely through the rock. The wedge thins from the outside in. The depth at which transformational faulting can occur, and where deep earthquakes can therefore originate, tracks the persistence of the wedge. And when the wedge is gone, when the last of the metastable olivine has finally converted, the conditions for this particular failure mode are gone with it, and the slab descends in silence from that point forward. This is one reason why not all subducting slabs produce deep earthquakes in equal abundance or at equal depths. A young slab, not long separated from the ridge where it formed, still warm, thin, losing its thermal contrast with the surrounding mantle relatively quickly, this slab may transform its olivine at or not long below 410 kilometres, leaving little or no metastable wedge to carry further down, and so producing few or no deep focus earthquakes. An old slab, cold and rigid and many kilometres thick, descending rapidly into the mantle before heat can diffuse into its core, this slab may carry its wedge very deep, approaching 600 kilometres or beyond, and may produce the deepest and largest deep focus earthquakes the planet makes. The geography of deep seismicity, the question of which subduction zones produce events at 500 or 600 kilometres, and which do not reach that deep, is in large part the geography of slab age and speed and thermal state, of how much cold the plate brings with it into the mantle, and how long the metastable wedge survives the descent. In the Japan slab, the seismic images show the wedge persisting to considerable depth, consistent with deep earthquakes occurring there at depths well into the transition zone. In the Tonga slab, arguably the fastest descending slab on Earth, and one of the oldest oceanic lithosphere reaching any trench, the deep seismicity is extraordinary in its abundance, and the metastable wedge inferred from seismic anomalies is correspondingly deep and thick. In the Mariana slab, again, the images are consistent with the model. These three regions are not proof. The seismic tomography that reveals them is an indirect technique, limited in resolution, sensitive to assumptions about the velocity models used to interpret it. But the convergence of the images with the predictions of the transformational faulting model is striking, and it is the convergence of predictions with observations in science that builds the kind of confidence that lets a hypothesis become, over time, an explanation. Not the only explanation. This is worth saying plainly. Because the Earth, which has had 4.5 billion years to arrange itself, and which operates at conditions no laboratory has fully replicated, does not always confine itself to a single mechanism. The history of deep earthquakes includes events that are harder to fit cleanly into the transformational faulting picture. Events that suggest another process may also be capable of breaking rock at these enormous depths, and that the two might sometimes work in concert and sometimes in isolation. The name of that alternative is thermal shear runaway, and its signature is different from the anti-cracks, and to understand it you need to look at the two great deep earthquakes in the catalogue side by side, the one that happened on 9 June 1994 in the deep subducting slab beneath the Altiplano of South America, and the one that happened on 24 May 2013, 609 kilometres beneath the cold waters of the Sea of Okhotsk. Together, they illuminate not just what deep earthquakes can do, but how much remains, still, quietly unresolved. The Bolivia earthquake came first, and in a sense that ordering matters, because it arrived in the catalogue as a kind of announcement, a declaration that the deep earth was capable of something that the instruments had never quite registered at that scale before, and that whatever was breaking down there, it was breaking in ways that did not simply match what the textbooks described for shallower ground. It was the 9th of June, 1994. The location was the Altiplano, that vast, cold, wind-scraped plateau that sits between the arms of the Andes in South America, a landscape so high and so dry that it seems, from the surface, to belong to another planet entirely. Beneath it, the Nazca Plate has been subducting eastward for tens of millions of years, diving under the South American continent at an angle, dragged down by its own weight, carrying the old seafloor of the eastern Pacific into the deep interior. And on that particular June morning, at a depth that seismologists would eventually settle at roughly 637 kilometres, something inside that slab broke. The magnitude was approximately 8.2. Before the events of 2013 that would eventually displace it, the Bolivia earthquake was the largest deep focus event ever instrumentally recorded, a record it held for nearly 2 decades. Seismographs around the world registered it. The signal arrived at stations from Alaska to Antarctica, from Japan to England, a clean, powerful waveform propagating outward through the body of the planet, and the scientists who read those records knew immediately that they were looking at something extraordinary. But what was most extraordinary about the Bolivia event was not simply its size, it was the character of its rupture. When researchers examined the seismic waveforms in detail and worked backward from the signals to reconstruct what the source had actually done, the picture that emerged was of a remarkably compact rupture. The area of the fault that had slipped was relatively small, far smaller than you might expect for an earthquake of that magnitude, and the stress drop, which is a measure of how much of the accumulated tectonic stress was released in a single event, was enormous. Enormous, stress drop, compact area, these two facts together imply something specific about the physics. They imply that a great deal of energy was released in a small space, and that much of that energy went not into the propagating seismic waves that travel outward and shake the ground, but into heat, into the rock itself. This is the signature that thermal shear runaway leaves behind. The name is almost self-explanatory once you hold it for a moment. Shear runaway, a process that feeds itself. Imagine a narrow zone inside the slab where slip has begun. Not along a pre-existing fault in the ordinary sense, but along some weakness, some incipient plane, something that has yielded first under the stress. As that zone begins to slip, the movement generates friction, and friction generates heat. The heat softens the rock in that narrow band, and softer rock, under the same applied stress, slips more easily, which generates more heat, which softens it further, which allows more slip. The process accelerates. It becomes a runaway. In the most extreme version of this scenario, the temperature in that thin shear zone rises so dramatically, so rapidly, that it crosses the melting point of the rock itself, and a thin film of melt is produced, a glassy, lubricating skin that reduces the resistance to slip almost entirely. That film of melt has a name in geology: pseudo-tachylite. It is found in ancient fault zones exposed by uplift and erosion at the surface, where geologists have recognized it as the frozen record of a past earthquake. A thin, dark streak of glass in the rock, the ghost of a moment of catastrophic shearing. And in the Bolivia event, the thermal and seismic evidence together suggests that something very like pseudotachylite may have formed at 637 kilometres depth inside a slab that had been sinking and cooling for millions of years. The slab was not cold everywhere. Cold at its core, yes, but the edges and the surfaces of the plate, where it makes contact with the warmer surrounding mantle, had been warming as the plate descended. Thermal runaway does not require the ambient rock to be particularly cold. It requires a concentrated stress, a narrow zone that begins to slip, and enough frictional dissipation to outrun the diffusion of heat into the surrounding material. If the shear zone is thin enough, the heat produced faster than it can spread away, and the runaway is possible. In the Bolivia event, everything appears to have conspired to produce exactly that. A concentrated, high-stress rupture in a compact zone, releasing its energy as heat at least as much as it released it as seismic waves propagating outward, leaving behind a record of a rupture that was, in a sense, almost violent in its compactness. A hot, brief, enormous release of stored stress in a very small volume of rock. Felt at the surface, the Bolivia earthquake was extraordinary in its reach. People across South America reported the shaking. Resonances were detected in structures far from the epicenter. And yet, and this is a theme that runs through all deep-focus earthquakes, regardless of their mechanism, the event caused essentially no destruction. No significant damage was reported. The depth was the shield, 637 kilometres of mantle between the rupture and the surface, 637 kilometres of hot, slightly yielding rock through which the waves had to travel, spreading out and attenuating as they went, losing energy at every kilometre of the journey upward. By the time those waves reached the base of the crust, they were already diminished. By the time they reached the surface, they were a shadow of what had been released. The earth had absorbed its own earthquake. And then there was the other one, the 24th of May, 2013. The Sea of Okhotsk, that grey enclosed body of water cupped between the Kamchatka Peninsula and the eastern coast of Russia. A sea that is cold even in summer and frozen in its shallower reaches through much of the winter. A sea that lies at the edge of the Pacific Ring of Fire, where the Pacific Plate has been subducting westward beneath the Eurasian and Okhotsk plates for as long as those plates have existed in their current configuration. And deep beneath that sea, at a depth of approximately 609 kilometres, something broke. The moment magnitude was approximately 8.3. It was and remains the largest deep-focus earthquake ever instrumentally recorded. It broke the Bolivia record by a fraction. But that fraction was enough. The Okhotsk event now stands at the top of the catalogue. The deepest great earthquake that has ever been measured, the loudest sound the deep earth has produced in recorded history. 609 kilometres. Pause with that number for a moment. the crust, the layer we live on, averages between 5 and 70 kilometres thick, depending on whether you are standing over ocean or continent. 609 kilometres down means the rupture occurred at a depth roughly 10 times the thickness of the continental crust. The slab that carried this earthquake had passed through the entire crust and the entire upper mantle and had descended well into the mantle transition zone before it broke. The rock that snapped had been in the upper mantle for long enough that the olivine at the slab's surface had already transformed through the sequence, already converted to wadsleyite, already pressed into ringwoodite, while the cold core, still protected by the thermal gradient, had held on, metastable, until it could not hold on any longer. The rupture was not compact. This is the first and most significant way in which the Okhotsk earthquake differs from the Bolivia earthquake, and the difference is scientifically important. Where the Bolivia rupture was concentrated in a small area with a very large stress drop, the Okhotsk rupture propagated along a fault surface roughly 180 kilometres long. 180 kilometres, a fault plane extending through the deep slab for a distance roughly equivalent to the distance between two large cities. And it ruptured fast. The rupture velocity was approximately 4 kilometres per second, comparable to the rupture velocities recorded in large shallow earthquakes, fast enough that some analyses placed it at or near the shear wave speed of the surrounding material, approaching what seismologists call supershear. A rupture travelling at or faster than the shear waves it is generating. The seismic equivalent of a sonic boom, a propagating break so rapid that the stress field barely has time to adjust before the rupture front has already passed. 4 kilometres per second through rock at 609 kilometres depth. Along a fault plane nearly 200 kilometres long. The rupture took roughly 45 seconds. Perhaps a little less or a little more depending on the model, and in those 45 seconds it radiated seismic energy outward in all directions, and that energy propagated through the mantle and through the transition zone, and upward through the upper mantle and through the crust, and out into the surface of the earth, spreading concentrically outward from a point beneath the cold sea. And then something did not happen. There was no tsunami. The earthquake was too deep. The rupture occurred entirely within the mantle, with no connection to the seafloor, no sudden displacement of the water column above, no wave. The enormous energy released by a magnitude 8.3 earthquake did not produce the oceanographic catastrophe that a shallower event of that size might have. The slab had simply broken too far down, and the water above it knew nothing of what had happened 600 kilometres beneath. And almost no one at the surface knew, either, not in the way that would have mattered, not in the way of shattered buildings or broken roads or coastal inundation. Reports came in from across Russia and from neighbouring countries of unusual sensations, a slow rolling, a faint and bewildering sense of movement in a place where no movement was expected. In Moscow, roughly 7,000 kilometres from the hypercentre, people on upper floors of tall buildings reported feeling something, a gentle, long-period swaying, the kind of motion that tall structures experience when very long seismic waves, the kind that only great earthquakes produce, set them resonating. 7,000 kilometres. Consider the scale of that journey. The seismic waves from a rupture beneath the Sea of Okhotsk, having already travelled 600 kilometres straight up through the mantle and crust, still carried enough energy at the surface to make a skyscraper in Moscow sway gently for a moment in the early morning. And then the moment passed, and nothing was broken. This is what it means to say that the deep earth has its own geography of consequence, its own relationship with the surface above it. A magnitude 8.3 earthquake that breaks at the surface is a catastrophe. Buildings collapse, ground liquefies, faults scarp the landscape, people die. The same magnitude breaking at 609 kilometres is a whisper at the surface, a gentle rocking of tall structures at 7,000 kilometres distance, a barely perceptible signal in the accelerometers of buildings that most people in those buildings would attribute to a heavy truck passing outside or to wind against the facade. The mantle absorbed the earthquake. The mantle, vast and slightly plastic, and hundreds of kilometres thick between the rupture and us, took the energy and spread it and attenuated it until there was almost nothing left by the time it reached the world we inhabit. Seismologists did not waste that whisper. The Okhotsk earthquake was, in a different sense, an extraordinary gift. A large, clean, well-recorded signal from 600 kilometres down, radiating from a rupture that was big enough to be read clearly at stations around the globe, but that did not create the surface complications, aftershock sequences on shallow faults, ground deformation, landslides, that sometimes make deep event analysis more difficult. Deep earthquakes radiate strong body waves, the P waves and S waves that travel through the body of the planet, with relatively little of the surface wave contamination that dominates shallow earthquake records. The Okhotsk event produced body wave records at thousands of stations, and those records have been analysed, modelled, and debated by researchers for years. The rupture velocity, the fault geometry, the stress drop, which was large but distributed over a large area, hence the heat per unit area was comparatively modest, unlike Bolivia. The question of whether the rupture approached supershear and what that implies about the mechanical properties of the rock at that depth. And then there were the aftershocks. Deep earthquakes, as a rule, are nearly silent after the main shock. The rock around the rupture zone is hot enough and the mantle ductile enough that the stress that drove the earthquake dissipates quickly through slow creep. The material flows rather than breaking again in smaller subsidiary events. The aftershock productivity of deep earthquakes is markedly lower than for shallow earthquakes of comparable magnitude, and this suppression of aftershock activity is itself evidence about the medium. A medium that responds to stress perturbations by flowing, not fracturing. The Bolivia earthquake had very few aftershocks. This fit the pattern. But the Okhotsk earthquake was different. It produced a notable aftershock sequence, scientifically remarkable precisely because it violated the expectation. Something about the rupture, or about the slab in which it occurred, or about the local stress state in the aftermath of the main shock, allowed subsidiary fractures to occur where the deep earthquake record generally does not permit them. The reasons for this are still being worked out. It is one more thread in the fabric of deep earthquake science that remains loose. One more place where the data insists on being more complicated than the simplest version of any model predicts. Two great deep earthquakes then, Bolivia and Okhotsk, both at depths greater than 600 kilometres, both magnitude greater than 8, both felt at vast distances from the epicenter, and both causing essentially no damage or loss of life. But in the character of their ruptures, they are not the same event. Bolivia is compact, hot, high-stress drop, consistent with thermal shear runaway, producing a film of melt in a narrow zone. Okhotsk is broad, fast, distributed, more nearly consistent with a fault-like propagation along a self-lubricating anti-crack zone, with a stress drop that is large, but spread over an area nearly 200 kilometres long. One event looks like a melt-lubricated implosion. The other looks, in some respects, like a very deep, very fast surface-style fault rupture. The honest statement of where the science stands is this: neither transformational faulting nor thermal shear runaway is, alone, the complete answer. The Earth uses what is available. In the coldest, fastest slabs, where the metastable olivine wedge has survived deepest and is primed for collapse, transformational faulting may dominate. In situations where a narrow zone has begun to slip and where the geometry concentrates stress into a small volume, thermal runaway may take over and accelerate the failure toward a compact, hot, melt-producing event. In some cases, both processes may operate in sequence or in concert, the anti-crack mechanism initiating the rupture. Thermal effects lubricating and sustaining it as it propagates. The two giant earthquakes in the catalogue represent different expressions or different mixtures of these possibilities, and the scientific work of distinguishing them continues. The Earth, which has been subducting plates and breaking them at depth for hundreds of millions of years, does not feel obliged to limit itself to a single mechanism simply because that would be tidier. What the comparison of these two events confirms, beyond any particular mechanism, is the reality of deep focus rupture as genuine earthquake failure, not an artifact of measurement, not a surface signal mislocated by a software error, but actual, large-scale, rapid failure of rock at 600 kilometres or more of depth, under pressures of 20 or more gigapascals, in a material that the ambient mantle around it would render ductile and flowing if it had access to the same temperature. The cold slab is the critical ingredient. It is the thermal anomaly in the deep mantle, the ribbon of old, stiff, cold oceanic lithosphere descending from the trench that preserves the conditions under which deep earthquakes are possible at all. Outside the slab, the mantle flows. Inside the slab, in its cold core, something can still break. And here it is, worth stepping back and considering the broader landscape of what breaks and at what depths. Because the distinction between deep focus earthquakes and the earthquakes that occur at shallower levels in the descending slab is not simply a matter of depth, it is a matter of mechanism, and the transition between mechanisms as depth increases is itself a story worth following. Between roughly 70 and 300 kilometres, the depth range that seismologists call intermediate. Between the shallow seismicity of the crust and the deep focus events below, there is a third category of earthquake, one with its own mechanism and its own relationship to the descending plate. These are the intermediate depth earthquakes, and the process most widely credited for their occurrence is called dehydration embrittlement. And it is worth understanding because it illustrates just how many different ways the descending slab manages to make the Earth tremble as it sinks. The oceanic lithosphere that enters a subduction zone at the trench is not simply a slab of dry rock. Over the tens of millions of years it spends at the seafloor before it begins its descent, it has been altered by seawater. Water circulates through the fractured basalt and peridotite of the oceanic crust and the uppermost mantle, reacting chemically with the minerals it encounters. The most significant product of this reaction in the upper mantle portion of the plate is serpentine, a family of hydrous minerals, minerals that have incorporated water into their crystal structures. Minerals that are physically weaker and seismically different from the unaltered olivine they replace. Serpentine takes the hydrogen and oxygen from seawater and binds them into its lattice, and in doing so, it changes the mechanical properties of the rock profoundly. The serpentinized portions of the slab are softer, weaker, and, crucially, they carry a significant mass of chemically bound water. Water that is not free to flow, but is locked inside the mineral structure itself. As the slab descends into the mantle and the temperature and pressure increase, those hydrous minerals become unstable. They break down. The water they had stored, the water that had once been seawater at the bottom of the Pacific Ocean perhaps, or the Atlantic, or the Indian, is released back into the mineral world as free fluid, as water molecules that are no longer bound into a crystal, but are moving, mobile, able to permeate the surrounding rock. And free water, under high pressure, does something important to fault mechanics. It raises what engineers and geologists call pore pressure. Pore pressure is the pressure of the fluid in the pores and fractures of a rock mass, and it works in opposition to the confining stress that is trying to clamp potential fault surfaces shut. The higher the pore pressure, the lower the effective normal stress on a potential failure plane, and the easier it becomes for that plane to slip. At intermediate depths, 70 to 300 kilometres, the temperatures are high enough to destabilize the hydrous minerals and drive off the water, but the material may not yet have reached the conditions of the full deep focus earthquake regime. What the dehydration does is temporary. It releases a pulse of water that briefly softens the fault zone, allows slip to occur that would otherwise be suppressed by the high confining stress, and produces an earthquake. Once the water has dissipated into the surrounding rock, absorbed into new minerals, carried upward by the pressure gradient, the fault zone is clamped shut again, and the seismic cycle moves on. Serpentine, the primary carrier of this water, has been studied extensively. It is weak, easily sheared, and it dehydrates in a range of temperatures that corresponds approximately to the intermediate depth earthquake zone. The spatial coincidence between where serpentine breaks down and where intermediate depth earthquakes occur is not perfect. The Earth is not perfectly obedient to simple models, but it is close enough and consistent enough across multiple subduction zones around the world that dehydration embrittlement is now the leading explanation for the intermediate depth category of seismicity. It is, in its own way, as elegant a mechanism as transformational faulting. The slab carries its water down, the water destabilizes the rock breaks, and the water is released to continue its journey deeper into the mantle, where it will be incorporated into new minerals or eventually recycled back toward the surface in ways that take millions of years to complete. Below 300 kilometres, the serpentine and the other common hydrous minerals of the uppermost plate have largely broken down. The free water has been released. What remains in the cold core of the slab is olivine, or, in its metastable form, olivine that should have transformed but has not, and the mechanisms available for fracture shift accordingly. Dehydration embrittlement fades as a candidate for true deep focus earthquakes because, below 300 kilometres, there is simply less free water available to do the work of reducing effective stress. The leading mechanism for the deepest earthquakes becomes instead the transformational faulting and thermal shear runaway discussed at length above. The transition is not perfectly sharp. There is likely a range of depths over which both mechanisms contribute, and some researchers have argued that high-pressure hydrous minerals stable to greater depths may carry water further down than the simple model suggests. But the broad distinction holds. The shallow earthquakes are driven by friction on existing faults. the intermediate earthquakes largely by dehydration embrittlement, and the deepest earthquakes by the phase transformation instabilities and thermal effects unique to the cold slab at extreme depth. 3 different mechanisms for 3 different depth ranges, all operating within the same descending plate, all part of the same continuous process of subduction. The slab that enters the trench at the surface breaks shallowly in the cold, brittle crust, trembles at intermediate depths as its hydrous minerals give up their water, and then, deeper still, quakes as its surviving olivine finally collapses into a denser form or as a thin zone of shear runs away into melt. The earthquakes are, in this sense, the biography of the slab, a record, written in seismic waves, of every stress and phase change and dehydration event that the descending plate undergoes on its journey downward. To read the earthquakes is to read the slab's history. And there is one more thing the seismographs tell us about that journey, something that comes not from the earthquakes themselves, but from the absence of earthquakes, from where the seismicity stops, and from what lies beyond. The 2 great events, Bolivia at 637 kilometres, Okhotsk at 609 kilometres, are near the bottom of the catalogue. Not quite at it, but near it. The deepest reliably recorded earthquakes occur at approximately 700 kilometres. Below that depth, the seismographs go quiet. Not because nothing is happening, something is certainly happening, but because the slab, whatever its remaining olivine had to give, has given it. The metastable olivine, if it survived this far, has transformed. The thermal gradient between the slab and the surrounding mantle has been eroding for the entire descent, and by 600–700 kilometres. The slab's interior is no longer cold enough to sustain the conditions that make deep seismicity possible. The rock warms toward the mantle temperature, it softens, it begins to flow rather than fracture. And the earthquakes stop. But the slab does not stop. Seismic tomography has traced these descending sheets of former ocean floor all the way toward the core mantle boundary, nearly 2,900 kilometres down, a distance so vast that the earthquakes, impressive as they are, illuminate only the first quarter of the slab's total journey. Below 700 kilometres, where the seismicity ends, the slab continues its descent in silence, warming, slowly losing its identity as cold lithosphere, becoming something more like the surrounding mantle in temperature, if not yet in composition, sinking through the lower mantle for tens of millions of years before it arrives, reformed and unrecognizable, near the base of the solid earth. The earthquakes are, in that sense, only the opening chapter of a story that ends in geological anonymity far below anything a seismograph will ever hear. But within that chapter, within the 700 kilometres of seismic biography the descending plate leaves behind, 2 events stand apart from everything else in the catalogue. 2 earthquakes so large and occurring so deep that they remain singular data points, studied and restudied, argued over and reanalyzed, each one teaching something the other does not quite confirm. The first arrived on the 24th of May 2013 beneath the Sea of Okhotsk off the Kamchatka Peninsula in eastern Russia. Its moment magnitude was approximately 8.3. Its hypercenter lay at roughly 609 kilometers below the surface. By those 2 numbers alone, it became the largest deep-focus earthquake ever instrumentally recorded, surpassing, after nearly 2 decades, the previous record holder from South America. And the way it ruptured was almost as remarkable as its size. The fault zone broke along a length of approximately 180 kilometers, and it did so at a rupture velocity of around 4 kilometres per second, a speed comparable to how a large, shallow, ordinary earthquake tears along a surface fault. Some analyses suggested the rupture approached or briefly touched what seismologists call supershear, a propagation speed at or above the shear wave velocity of the surrounding rock, a regime more commonly associated with shallow strike slip faults where the geometry is clean and the material is cold and uniform. At 600 kilometres deep, in the interior of a descending slab, that speed was not expected. And yet the Sea of Okhotsk earthquake, for all its extraordinary size and depth and rupture velocity, caused essentially no destruction. No buildings fell. No one died. There was no tsunami because the energy, generated so far below the seafloor, had to travel through hundreds of kilometres of mantle and crust before reaching the surface. And by the time it arrived, it had spread and attenuated and dispersed into something the Earth absorbed without visible consequence. The seismic waves did reach the surface, and they propagated outward across a continent, and they were faint but measurable thousands of kilometres away. Moscow, roughly 7,000 kilometres from the epicenter, recorded a tremor, not a destructive one, a whisper. A faint mechanical signal arriving across Russia from the deep interior of the planet, from a rupture that had occurred where no human presence exists, and no human presence will ever reach, at a depth where the pressure is approximately 20 to 24 gigapascals and the surrounding rock temperature approaches 1,500 degrees Celsius or more. The rupture was large, and its heat production per unit area was comparatively modest. It behaved, in some ways, more like an ordinary fault rupture than like the kind of compact, intensely energetic deep earthquake that theoretical models of transformational faulting would most purely predict. The fault zone broke broadly and fast, like a wound opening, and the shear was distributed across that long 180-kilometre plain rather than concentrated into a small, intensely heated point. The second great event had come 19 years earlier, on the 9th of June 1994, beneath the Altiplano of Bolivia, at a depth of approximately 637 kilometres. Its moment magnitude was approximately 8.2, slightly smaller than Okhotsk, though the difference is almost negligible at that scale. Before 2013, it held the record, and in its character it was strikingly different from the earthquake that would eventually surpass it. The Bolivia earthquake ruptured a far more compact area. Its stress drop was very large, meaning the fault released an enormous amount of stored elastic energy relative to its rupture dimensions. The heat generated per unit area of that fault zone was correspondingly immense. The geophysical evidence for that event is consistent with what is called thermal shear runaway, or shear heating instability, a process in which the initial slip on a narrow fault zone generates frictional heat. That heat softens the rock and concentrates further slip into the same narrow band, which generates more heat, which softens the rock further, in a feedback that accelerates until a thin film of molten rock, what geologists call pseudo-tachylite, forms along the fault and lubricates the remaining motion. The rock in that thin zone melts, not because the ambient temperature at 637 kilometres is high enough to melt it, it may not be, but because the mechanical energy of the earthquake itself, focused into a narrow shear zone, generates enough local heat to briefly liquefy a layer perhaps millimetres or centimetres thick. which then allows the slab to finish tearing through a medium that is, for a fraction of a second, fluid. Here, then, are two earthquakes of almost identical magnitude and almost identical depth, and they did not fail in the same way. One broke broadly and fast, approaching supershear across a long fault. The other broke compactly and hot, with evidence of melt. The science does not yet offer a clean resolution to that difference, whether both events express different proportions of the same mechanisms, or whether the geometry of the slab in each location favored a different failure mode, or whether the thermal history of the olivine in the Kamchatka slab and the South American slab differed enough to produce genuinely distinct outcomes. The honest position is that both mechanisms, transformational faulting and thermal shear runaway, are supported by laboratory evidence and consistent with aspects of the seismic record, and that the two great earthquakes together suggest the deep slab does not fail in only one way. It is worth pausing here, briefly, to note that a third mechanism operates at shallower depths. Between roughly 70 and 300 kilometres, the range that seismologists call intermediate depth, and that mechanism is different again. As the slab descends through those upper reaches, the seafloor rock it carries has been altered by seawater over millions of years of ocean floor exposure. Minerals like serpentine have formed in cracks and fractures, locking water into their crystal structure in the form of hydroxyl groups. Under increasing heat and pressure, those hydrous minerals break down and release that bound water as free fluid. The fluid raises the pore pressure inside the rock, reducing the effective normal stress, clamping the fault surfaces together, and allowing slip even under high confining pressure. The mechanism known as dehydration embrittlement. It is elegant and well supported and explains a great deal of the intermediate depth seismicity that occurs as the slab first descends past the crust and into the upper mantle. But at 600 kilometres, that water is gone. Serpentine breaks down long before the slab reaches such depths. What remains at those depths is something altogether different. What remains is the cold, ancient structure of the slab itself, the compressed geometry of olivine in its metastable form, the thermal memory of seafloor that has not seen the ocean surface in tens of millions of years, and whatever rupture physics arises from the meeting of extreme pressure and a crystal lattice that has quietly refused to obey. But to understand what the earthquakes are, to understand what they are doing inside the planet, and why they form the particular shapes and patterns they do, it is necessary to step back from the individual events and look at the whole arrangement. Because the deep earthquakes do not scatter randomly. They are not distributed by chance through the mantle like sparks thrown into a dark room. They trace something. They trace a shape, and that shape is one of the most important pieces of evidence in the entire history of the earth sciences. Plot every deep earthquake on a cross-section of the earth, from the ocean trench at the surface down into the mantle below, and you will see a line. Not a perfectly straight line, but a coherent, inclined zone of seismicity dipping down and inward from the trench at an angle, descending progressively deeper as it moves away from the ocean floor and into the interior. The earthquakes are not simply occurring at random depths below a piece of seafloor. They are occurring inside a structure, a planar slab of material that is descending into the mantle along a defined path, and they are occurring because that slab still has enough cold, rigid integrity to break rather than flow. The earthquakes are the sound of the slab. They are the sound of old seafloor being dragged through the mantle, kilometre by kilometre, under pressures that would crush any ordinary intuition about what rock can do. This inclined zone of seismicity has a name. It is called the Wadati-Benioff zone, and the name carries inside it a century of science and a story about how slowly the Earth gives up its secrets. Kyo Wadati was a Japanese seismologist working in the 1920s and 1930s, in an era when the prevailing understanding held that earthquakes were a phenomenon of the crust, of the thin outer shell of the planet, where rock was cold and brittle and capable of fracturing. The assumption was reasonable by the standards of the time. The crust was the only layer anyone thought could break. The mantle was imagined, insofar as it was imagined at all, as something too hot and too plastic to do anything so sudden as rupture. And then Wadati, analysing the data from Japan's growing seismograph network, found earthquakes that did not fit. Earthquakes whose waves arrived with the timing signatures of sources far below the crust, far below the surface geology, far below anything that orthodox theory said should be capable of seismicity. He documented them carefully and systematically, demonstrating that they were not instrument error, not misreadings, not artifacts of a young science learning its own limits. They were real. Deep earthquakes existed, and the prevailing intuition was wrong. The world of seismology absorbed this slowly, as such adjustments tend to be absorbed, and the work might have remained a regional curiosity were it not for the American seismologist Hugo Benioff, who in the 1940s and 50s independently characterized the same inclined planes of seismicity beneath the Western Pacific and the Americas. Benioff recognized that these dipping zones had a coherent planar structure, that the earthquake foci were not scattered randomly with depth, but were organized along planes that descended from the surface at consistent angles. The observation was precise and durable, it survived scrutiny, and it sat, waiting, until the 1960s, when the earth sciences underwent the most profound reorganization in their history. In 1968, Brian Isaacs, Jack Oliver, and Lynn Sykes published a study in the Journal of Geophysical Research that took the inclined seismic zones, placed them inside the new framework of plate tectonics, and showed what they were. The Wadati-Benioff zones were descending lithosphere. The inclined planes of seismicity were the physical traces of old oceanic plates sinking back into the mantle at subduction zones. The earthquakes were not mysterious anomalies occurring somewhere beneath the crust for unknown reasons. They were signatures of a specific, coherent mechanical process, the recycling of oceanic plates into the deep interior of the planet. Wadati and Benioff had found the seismic signature of subduction years before the word subduction existed in its modern sense, and it was only when plate tectonics arrived to provide the framework that the full meaning of what they had measured came clear. The slab, then, the old oceanic lithosphere that forms the floor of the deep ocean, is dense. It forms at mid-ocean ridges, where mantle material wells up, cools, solidifies, and spreads outward. As it spreads and moves away from the ridge over millions of years, it cools further, thickens, and grows denser. Old oceanic crust is significantly denser than the mantle rock beneath it, and it is this density that drives subduction. At the trench, where the old seafloor encounters the margin of a continent or another plate, it bends downward under its own weight and begins to sink. It does not fall freely. It descends slowly, pulled by gravity over millions of years, dragging the surface plate behind it. And as it descends, it carries with it everything it has accumulated, the chemistry of ancient seafloor, the mineral transformations that occurred at the ocean ridge where it formed, and the thermal history of its long transit across the ocean basin. That thermal history matters enormously because the slab descends into a mantle that is much hotter than the slab itself. The surrounding mantle at 500 or 600 kilometers depth is at roughly 1500 to 1600 degrees Celsius. The interior of a cold, old, fast-sinking slab can be hundreds of degrees cooler than that. Some estimates place the temperature difference in the coldest parts of the fastest slabs at 500 to 800 degrees Celsius. The slab is, in geophysical terms, frigid. It is a blade of cold descending through warmth, and that thermal contrast is not a side detail, it is everything. The cold is what keeps the olivine metastable. The cold is what prevents the transformations from running on schedule. The cold is what allows the slab to remain rigid enough to fracture where the surrounding mantle, at equilibrium temperature, would simply flow. Remove the cold, and there are no deep earthquakes. The cold is the engine of the whole phenomenon, and the earthquakes that the cold slab generates as it descends trace its shape with remarkable fidelity. Each earthquake marks a point where the slab broke. Each hypocenter is a point on the geometry of the descending plate, fixed in space by the seismic waves it radiates and retrieved by the global network of seismographs. Map enough of them, and you have, in effect, a tomographic image of the slab itself, its angle of descent, its lateral extent, its depth, its continuity or lack of it. The Wadati, Benioff zone, is the slab, made audible, but the distribution of the earthquakes along the slab is not uniform with depth, and that non-uniformity carries its own information. If you look at the global catalogue of deep-focus seismicity and sort the events by depth, a distinctive pattern emerges. Activity is reasonably common from 300 kilometers down to about 450. Then it thins noticeably through the 450 to 500 kilometer range. Then it revives, rising again to a second peak somewhere near 550 to 600 kilometers, and then it cuts off. Not gradually, not with a slow fade-out into occasional scattered events, but sharply. Essentially, no earthquakes are recorded below approximately 660 to 700 kilometers. The deepest reliably located events cluster near that boundary, and then they stop. This distribution is bimodal, two clusters of activity separated by a quieter interval, and the bimodality is not random. It reflects the mineralogy of the slab at depth. The lower cluster, the one peaking near 550 to 600 kilometers and cutting off near 660, corresponds to the deepest part of the Mantle transition zone and to the region where the olivine to ringwoodite transformation, delayed in the cold slab to depths it would not reach in warmer material, is finally running and finally providing the anti-cracks and the metastable wedge collapses that generate the deepest earthquakes. And the abrupt termination near 660 kilometers is not a coincidence. 660 kilometers is a boundary. It is the boundary where ringwoodite itself can no longer survive. Below this depth, even ringwoodite, the denser spinel structured form that olivine becomes in the transition zone, breaks down into a pair of even denser minerals, bridgmanite, sometimes called silicate perovskite, and ferropericlase. This transformation defines the base of the Mantle transition zone and the top of the lower mantle, and it is a transformation with a particular thermodynamic character that makes it a significant barrier for descending slabs. The olivine to wadsleyite transition near 410 kilometers releases heat as it runs. It is exothermic, and for a cold slab descending through that depth, This means the transition boundary is deflected downward, the slab crossing it slightly deeper than the surrounding mantle. But the ringwoodite to bridgemanite transition near 660 kilometres is different. It is endothermic. It absorbs heat rather than releasing it, and this gives the phase boundary a negative Clapeyron slope, meaning that, for cold material, the transition boundary is deflected upward toward shallower depths rather than deeper ones. For a cold slab trying to punch through this boundary into the lower mantle, the boundary actively opposes it. The phase transition itself resists the slab's descent. This resistance has consequences that are visible in seismic tomography. The technique that uses the travel times and waveform distortions of seismic waves passing through the Earth to build up three-dimensional maps of the interior, the way a medical scanner uses X-rays to build up images of the body. Tomographic images of the mantle beneath Japan and beneath parts of the Western Pacific show something remarkable: slabs that have descended into the transition zone, reached the 660 boundary, and then stopped. Not continued downward, but instead spread out laterally, lying flat against the underside of the boundary in a kind of pool of cold material, stagnating there rather than punching through. The slab has been resisted by the endothermic phase change, the negative Clapeyron slope of the 660 discontinuity, acting as a kind of floor that the cold material cannot easily cross. Some slabs stagnate in this way and appear to accumulate in the transition zone for a long time before eventually, in some cases, sinking further. Others, in other subduction zones, appear to punch through. The tomographic images show continuous cold anomalies descending below 660 kilometres into the lower mantle. And when a slab sinks below 660 kilometres, the earthquakes stop. The slab is still there. The cold material is still descending, still sinking through the lower mantle toward the deep interior. But it no longer generates earthquakes that we can detect. The olivine is gone. It has transformed to bridgemanite and ferropericlase under the conditions of the lower mantle. The metastable wedge, the blade of untransformed crystal that was the engine of the deep seismicity, cannot persist below the transition zone. Whatever mechanism remains for brittle failure, or whether any such mechanism remains at all, the evidence suggests that below 700 kilometres the planet becomes seismically silent, at least on the scale of the earthquakes the global network can confidently locate and report. The slab sinks on, warming gradually as it descends through hundreds more kilometres of lower mantle, but it does so without making a sound we can hear. The earthquakes are, in this sense, the visible portion of a much longer journey. A journey that begins at the ocean surface, at the mid-ocean ridge where new seafloor is born, and that ends, eventually, after tens of millions of years of transit across the ocean floor and then descent through the mantle, somewhere near the base of the mantle itself, at the core. Mantle boundary nearly 2,900 kilometres below the surface. Seismic tomography has revealed the traces of slabs sinking all the way toward that boundary, appearing as cold, anomalously fast wave-speed material threading down through the lower mantle in ghostly streaks. These structures are sometimes called slab graveyards, the accumulated remnants of ancient subducted plates that sank long ago and are still, improbably, distinguishable by their thermal and chemical signatures even after hundreds of millions of years of slow thermal diffusion and mantle flow. The earthquakes illuminate only the top 700 kilometres of this journey. They are the first chapter. Below that, the slab continues in silence, a cold sheet warming millimetre by millimetre in the surrounding mantle over geological timescales, until eventually it reaches thermal equilibrium with its surroundings, loses its identity as a distinct cold structure, and is assimilated. The olivine that rode down from the ocean surface and transformed, kilometre by kilometre, through wadsleyite and ringwoodite and finally into bridgmanite and ferropericlase, is recycled. The atoms of iron and magnesium and silicon that once formed the mineral structure of ancient seafloor are returned to the deep mantle, from which new mantle material will eventually rise again at a mid-ocean ridge somewhere and form new seafloor. The planet is eating its own old ocean floor and returning it to circulation. It has been doing this for billions of years. The deep earthquakes are the sound of that process, the audible portion, the small fraction of the whole that happens to involve crystal phase collapses and sheer instabilities energetic enough to send waves to the surface and be recorded. There are places on Earth where this process runs with particular intensity, where the geometry and history of subduction have conspired to produce the greatest concentration of deep-focus seismicity anywhere on the planet. The Tonga Kermadec subduction zone in the southwestern Pacific is that place. The Tonga Trench is one of the deepest in the world, and the Pacific Plate descending into it is old and cold and fast, conditions that maximize the preservation of the metastable olivine wedge and the generation of deep earthquakes. Tonga alone accounts for the majority of the planet's deep focus seismicity. Well over half of all the deep earthquakes recorded globally occur in or near this single subduction system. The zone extends southward from Tonga through the Kermadec region, and it produces deep earthquakes with a frequency and magnitude that make it, in this particular phenomenon, the most productive corner of the Earth. The Kamchatka arc, beneath which the Great Sea of Okhotsk earthquake of 2013 occurred, is another of the major deep earthquake zones, along with the Japan arc. The Mariana Trench and its southward extension toward the Izu-Bonin region and the South American subduction zone beneath Peru and Bolivia, the zone that produced the Bolivia earthquake of 1994. Each of these systems represents old, cold, oceanic lithosphere descending into the mantle. Each carries a version of the metastable olivine wedge, and each produces, from time to time, the deep ruptures that come up through hundreds of kilometres of mantle and announce themselves faintly to the seismographs of the world. The geography of deep seismicity is, in a very direct sense, the geography of subduction. To know where the deep earthquakes are is to know where the planet's recycling machine is working. And the recycling machine does not carry only rock. This is one of the more remarkable things that research into the deep earth has revealed in recent decades, and it reframes the subduction of old seafloor as something stranger and more consequential than the simple recycling of cold crustal material. The slab carries water. Not water in the sense of a liquid at the depths and pressures involved, but water in the sense of hydrogen and oxygen atoms bound into the crystal structures of the minerals inside the slab, waiting in the lattice until the conditions of the deep mantle either release them or transform the mineral into something that holds them differently. The story of this water is told most vividly by a tiny mineral grain discovered inside a diamond. In 2014, Graham Pearson and his colleagues reported on a natural ringwoodite inclusion trapped inside a diamond retrieved from duna in the state of Mato Grosso, Brazil. Diamonds form at high pressures in the earth and can trap fragments of the surrounding material inside them as they grow. preserving those fragments at the pressure and temperature conditions of their formation as the diamond rises eventually to the surface in a volcanic eruption. The diamond from Juna had formed at transition zone depths. The pressure fingerprint was consistent with formation at somewhere between 400 and 700 kilometres, and the ringwoodite inclusion trapped inside it contained, by spectroscopic analysis, roughly 1 to 1.5% water by weight, bound into the mineral as hydroxyl groups incorporated into the crystal structure. This was the first time a natural sample of a transition zone mineral had ever been recovered from the Earth's interior, and what it said was significant. If ringwoodite in the transition zone can hold that much water in its structure, and this was not a laboratory synthesis, but a natural sample from the Earth itself, then the transition zone, stretching from 410 to 660 kilometres depth, may hold an enormous mass of water in bound mineral form. Some estimates based on this and related work suggest the transition zone could contain water equivalent to several times the volume of the world's oceans, locked in the crystal structures of wadsleyite and ringwoodite. The planet's water budget, understood for so long primarily as a surface and shallow crust phenomenon, may have a vast, deep component. And subducting slabs are the mechanism that carries water into this reservoir. The altered seafloor rock of the slab, the serpentine and other hydrous minerals that form at the ocean floor through the interaction of basalt with seawater, breaks down at intermediate depths and releases some of its water, feeding the fluid that drives dehydration embrittlement in the shallower part of the slab. But not all of the water is released so easily. Some is carried deeper, bound into mineral structures that survive to greater depths, and the slab acts as a conveyor belt, delivering hydrogen and oxygen from the surface ocean to the deep mantle. The descent that produces the deep earthquakes is also a descent that may, over the billions of years of Earth history, have shuttled water between the surface and the interior in quantities that shape the whole hydrological system of the planet. This connection between the deep earthquake process and the water cycle of the Earth is still an active area of research. The details are contested, the quantities are uncertain, and the ringwoodite inclusion from Juna is a single data point. Remarkable, but not yet the final word. But it is the kind of connection that the study of deep earthquakes keeps producing, a phenomenon that begins with a seismograph needle trembling in response to a distant shock, and that unfolds as the science deepens into something much larger and more encompassing than the original questions suggested. You ask why rock breaks at 600 kilometres. You end up asking how the surface ocean is connected to the deep mantle. The earthquake is a thread, and the thread runs further than it first appears. There is something else worth noting about what the deep earthquakes are, by contrast with what they are not. They are not, in any usual sense, dangerous. The Sea of Okhotsk earthquake of 24 May 2013, moment magnitude approximately 8.3, the largest deep-focus earthquake ever instrumentally recorded. That shock caused essentially no structural damage and no tsunami. The energy radiated by the rupture of a fault, approximately 180 kilometers long, propagating at roughly 4 kilometers per second through material 609 kilometers below the surface, had to travel upward through that entire column of mantle and crust before it could reach any inhabited place. By the time the waves arrived at the surface, they had spread through an enormous volume of rock, losing energy to distance and to the imperfect elasticity of the mantle through which they passed. They were felt faintly, felt in Moscow, more than 7,000 kilometers away, which is itself an extraordinary fact about the carrying power of body waves through the Earth's interior. But felt is not harmed. Not a building fell. Not a coastline was inundated. The earthquake was felt across a continent and registered on seismographs across the world, and in terms of human consequence, it was essentially silent. This is the strange character of the deepest earthquakes. They are giants by the measure of energy released, and they are nearly invisible by the measure of human experience. They live entirely in the deep interior. They rupture rock that no human being has ever seen and no instrument has ever directly sampled. They send their energy upward through hundreds of kilometres of mantle, and by the time that energy arrives at the surface, it is a faint trembling in sensitive instruments. A barely perceptible swaying felt by people in tall buildings in cities far from the epicenter, a line on a seismogram that tells, to those who know how to read it, an extraordinary story about where the trembling came from and what kind of material it passed through on its way up. The deep earthquake is, in this sense, the planet's own self-reporting. The mantle cannot be sampled directly. The transition zone at 500 kilometers depth is as inaccessible as the surface of another world. No drill has come close. No mine reaches a fraction of the way. No direct measurement of pressure or temperature at those depths has ever been made in situ. What the Earth's interior looks like at those depths is known almost entirely through inference, through the behavior of seismic waves sent down by earthquakes and retrieved by seismographs, through the high-pressure laboratory experiments that reproduce the mineral physics of the deep mantle in small capsules, through the thermodynamic modelling that predicts which crystal structures are stable under which conditions. The deep earthquakes are not incidental to this knowledge. They are central to it. Their body waves, the compressional P waves and the shear S waves that propagate through the Earth's interior, travel through the transition zone and the upper-lower mantle and are changed by what they encounter there. The 410 and 660 discontinuities that define the transition zone are known as discontinuities precisely because they produce reflections and conversions in the seismic wave field, and deep earthquakes, because they occur below the complicated and noisy shallow crust, are particularly clean sources of seismic energy. Strong, clear signals with relatively little of the surface wave complexity that makes shallow earthquakes harder to analyze at depth. Much of what is known about the structure of the mantle transition zone, about where exactly the phase boundaries sit and how they vary laterally, has been determined using the waves from deep earthquakes as the source. The planet speaks through these ruptures, and the seismologists who place their instruments in the ground and wait for the signals are listening to a conversation that the Earth has been having with itself for as long as oceanic plates have been subducting, which is to say, for hundreds of millions of years at least, and perhaps for most of Earth's history. The slabs that have descended and been swallowed, the olivine wedges that collapsed and produced their anticracks, the thin films of sheer melt that glided along for seconds in the Bolivia slab in June of 1994. The broad fast rupture that propagated through 600 kilometres of depth beneath the Sea of Okhotsk on a May morning in 2013. All of these are individual moments in a continuous, geological process that operates on timescales so vast that any individual earthquake, however large, is a single note in a very long piece of music. Consider for a moment the age of the seafloor that descends at a subduction zone. The Pacific plate that feeds the Tonga Trench is old, in some regions more than 100 million years old. meaning that the olivine crystals now being compressed and transformed and occasionally ruptured in the transition zone beneath Tonga began their existence as magma rising at a mid-ocean ridge more than 100 million years ago. They cooled and solidified into the floor of the Pacific Ocean long before the continents were in their current configurations. Long before the mass extinction at the end of the Cretaceous, long before any human lineage existed. They have spent 100 million years moving slowly across the Pacific Basin, a few centimeters a year, carrying the accumulated chemical memory of that entire transit. And now they descend into the mantle, kilometre by kilometre, and they break. And the breaking sends waves to the surface that are recorded on instruments built by a species that has existed for the blink of an eye in the timescale of the rock it is listening to. This is the larger picture that the deep earthquakes open when you follow them far enough. They are not simply a puzzle in seismology, not simply an anomaly to be explained by the right mineral physics mechanism and then set aside. They are windows into a planetary cycle, the cycling of crustal material from creation at mid-ocean ridges to destruction at subduction zones, from the surface ocean through the transition zone to the deep lower mantle and the slab graveyards, and eventually, over hundreds of millions of years, back to the mantle from which new magma will eventually rise. The Earth is not a static object. It is a machine, old beyond ordinary comprehension, running continuously, and the deep earthquakes are one of the places where that machine announces itself to the surface, where the slow, immense work of the interior briefly makes itself audible to those of us living on the thin, cool shell above. The Wadati, Benioff zones, those inclined planes of seismicity that Kiyo Wadati traced in the 1920s and Hugo Benioff mapped in the 1940s, and that Isaacs, Oliver and Sykes placed inside their proper context in 1968, are in this light something more than seismic curiosities. They are the visible edges of the planet's recycling mechanism. They are the outlines, drawn in earthquake foci, of the sinking plates. They are the record of work being done on a scale and over a duration that have no parallel in human experience, and they are recorded with exquisite precision by the global network of seismographs that human beings have placed in the ground over the last century, listening without fully understanding, gathering data that will take generations of scientists to fully interpret. And still there are things that the earthquakes do not tell us. The slab below 700 kilometres sinks silently, warming by imperceptible degrees over millions of years. The slab graveyards near the core mantle boundary are visible in tomographic images as cold, anomalously fast material. But what happens to them there? Whether they accumulate and eventually heat and are incorporated into mantle convection currents that rise back toward the surface. Whether they are chemically modified by the extraordinary conditions at the boundary between the silicate mantle and the liquid iron core. All of this is still being worked out, still being modelled and debated, still at the frontier of what the science can say. The earthquakes illuminate the beginning of the journey. The end is darker, quieter, and much less well understood. There is something fitting about that. The deep earth withholds more than it reveals. What we know is extraordinary, the mineral physics of olivine's transformation, the mechanics of the anticrack, the thermal conditions of the descending slab, the geometry of the Wadati. Benioff zone, the clean seismic signals of the 2013 Okhotsk earthquake, and what they told us about a fault rupturing at 609 kilometres depth. But what we know is the beginning of a question, not the end of one. The slab descends beyond the reach of earthquake seismology, beyond the depth where any currently imaginable instrument could follow it, and does whatever it does in the lower mantle in the dark, over timescales that dwarf the existence of our species. The planet is older than we are good at imagining. The process that produces these deepest earthquakes has been running, in various forms, since long before anything lived on the surface above it. And it will continue long after whatever instruments we have built have been worn away, and the rocks that contain their record have themselves been subducted into the mantle and recycled into something new. The next time you feel the ground move, wherever you are in the world, consider for a moment what lies beneath. Not just the soil and the bedrock and the familiar geology of the shallow crust, but further, through the Mohorovi discontinuity, into the upper mantle, through the olivine-bearing rock that deepens toward the transition zone, through the 410-kilometre boundary where the olivine becomes wadsleyite and the density increases. Deeper still, through the transition zone to the 660 boundary, where the ringwoodite gives way to bridgemanite, and ferropericlase and the lower mantle begins. And somewhere, in some part of the world where the Pacific Plate, or the South American Plate, or the Philippine Plate is descending into the mantle beneath a trench, a cold slab is working its way downward, carrying its metastable olivine wedge, carrying its bound water, carrying the chemical memory of 100 million years of ocean floor. And it may, at any moment, produce another deep earthquake, another rupture at 4 or 5 or 600 kilometres depth that sends body waves upward through the mantle, through the crust, to the surface, where they will spread across the planet and arrive, faint and precise, at the seismographs we have placed in our expectant listening network. The planet is not still. It has never been still. Beneath the quiet surface, beneath even the shallow seismicity of the crust, where the familiar earthquakes occur, the old seafloor is being dragged downward, and the deep mantle is receiving it, kilometre by slow kilometre, in a cycle that has no human time frame and no human analogue. And the earthquakes that announce this process, the deep focus ruptures at 300, 400, 500, 600 kilometres, are among the most extraordinary natural phenomena the planet produces. They are paradoxes that became, with enough careful science, not quite paradoxes but mechanisms, a crystal that refuses to transform until the moment it cannot refuse, and then collapses all at once, and tears. If you are somewhere in the world tonight, lying still, letting the weight of the day settle, there is a seismograph somewhere nearby, perhaps hundreds of kilometres away, perhaps less, recording the continuous quiet trembling of the earth. Not earthquakes necessarily, just the background noise of a living planet, ocean waves pressing on the seafloor, wind loading the crust, the faint hum of distant industrial machinery. Seismologists call it ambient seismic noise, and it is constant and global, and buried inside it, from time to time, is a signal from somewhere deep. A body wave that has arrived from the other side of the planet or from hundreds of kilometres underground, and that carries inside its waveform the fingerprint of a rupture that occurred in the cold heart of a slab, where olivine finally collapsed into something denser, and the planet briefly, faintly, announced what it was doing. Where in the world are you listening from tonight? The question is genuinely one I find myself thinking about, knowing that someone, somewhere, is lying in the dark in a city above a subduction zone, or in a place far from any trench, or somewhere entirely unexpected, and that the same planetary process, the same deep recycling machine, connects the ground beneath all of those places, even if some are closer to its most audible expressions than others. If you feel moved to share where you are, the comments are there, and I read them. The passages of deep rock are quiet now. The slab descends in the dark beneath the Sea of Okhotsk, beneath the Tonga Trench, beneath the Bolivia Altiplano, and it will descend whether we are watching or not. The science that has revealed it, the seismographs, the laboratory experiments, the tomographic maps, the diamond from Juna with its ringwoodite inclusion and its bound water, is still young, still accumulating, still finding in these ancient ruptures things it had not expected to find. That is not a failure. It is the normal character of a deep question. Each answer opens the next question a little further, and the ground beneath remains stranger and more intricate than any simple account of it can hold. You do not need to hold it all tonight. The olivine has been transforming since long before this night. The slab will still be descending in the morning. The earthquakes will come when they come, clean and precise and harmless at this depth, announcing a process too slow and too vast to worry about and too remarkable to ignore. You have followed the slab from the ocean surface to 600 kilometres and deeper still, into the silence below the deepest earthquakes, where the rock warms and changes without breaking and the planet takes back what it made. That is enough for tonight. Let the mantle do its work without you for a few hours. History will still be here in the morning. For now, rest.